process monitoring techniques for quality prediction in additive manufacturing, but more specifically laser powder bed fusion. A little bit background of myself. I completed my PhD in 1998 at Ohio State University in Net Shape Manufacturing Research Center. And since then, I advised many PhD students, master's students, and I was also part of the European Union project. I hosted 10 visiting doctoral and master's students. And then primarily I have books on manufacturing processes, micro manufacturing, intelligent machining, biomedical device manufacturing, design manufacturing, and modern manufacturing processes. Since 2014, I'm involved in additive manufacturing processes. These are metal additive manufacturing primarily, laser powder bed fusion. I'm also interested in laser material processing, laser-induced surface structuring, and primarily understanding process structure property relationships. And my background is also in metal cutting and machining processes, finite element simulation modeling especially. So I understand the challenges associated with numerical modeling and simulation. So I took my expertise into the metal additive manufacturing area. Also interested in process monitoring and control, because I think, you know, when you have models, when you have measurements, that's really a good connection. I don't know how we jump to this slide. Okay. Yes. So additive manufacturing essentially centers around being able to experiment the process through process monitoring and thermal measurements and physics-based simulation models, and also using both for generating model and correcting the model continuously for quantification of variability and uncertainty in powder bed fusion process. There are lots of variability and uncertainty in this process, so this is really needed. In fact, what we built is a metal product, but with a lot of complexity. So microstructure and material characterization, in order to understand the process parameters and the product effects, very important. Process chains and the role of monitoring in this framework is as follows. Essentially, we have four major components going into the additive manufacturing build job. We have a CAD data, we have powder material data, we have part build data, and part build or number of parts to be built job data. And then where it takes place, we have the machine. A machine is calibrated and there is a condition monitoring, and also process. Process is where the products are built, and process monitoring is essential. I'm going to dive into this group very much in detail. And then we have the post-processing because we don't really obtain finished products with this process. Heat treatment is essential, and also there are many other steps following the post-processing. Done either on-axis detection, which means that laser is used for also detecting what's going on the laser material interaction, or it could be off-axis detection by looking at the process using some sensory devices such as cameras and also pyrometers. And optical tomography is one of them. So you can see here that the camera is viewing the entire powder bed, but also viewing the Meltpool area. Now, here are the challenges, measurement and modeling for process monitoring and control. How can the system be measured in real time? Can it enable uncertainty quantification? Because that's very important to be able to quickly quantify and certify. Can precision of a measurement be certified? Can measurement data be employed to understand the full state of a system? Can mathematical statistical methods could be applied? Measured in situ and in line, what are the main challenges in on-axis and off-axis sensing in terms of accuracy, frequency, spatial, and temporal resolution. What is the correlation between process signature and product defects? How does the probability of detecting flaws connect with the quantification of an additively manufactured item? How can models and solutions be used to transfer the knowledge from the machine to machine, from laboratory to laboratory? And does this change depending on the material and geometry? What are the impacts of false positive or false negatives? And what is the economical advantage of in-situ monitoring? Does it even have economical advantage? And what are the challenges moving forward, monitoring to the feedback control to correct the system? So to answer all of those questions in the metal additive manufacturing world, we conducted many projects and we published many papers on that. I can group those into several slides. One of them is modeling. Modeling is essential to understand what are the thermal models, tell us the temperature distribution, where should be expected Meltpool to take place, and what are the temperature effect around it. In fact, another model is the process simulation results and a microstructure model, solidification microstructure. Process monitoring and control is essential, right? We talked about that. Here's an example for off-axis. Off-axis camera monitoring to detect the Meltpool and as well as the spatter, and then control the process for over-melting and under-melting. So I will actually talk about that slide more. And off-axis analysis, offline analysis, offline quality predictions include looking at the surfaces and identify the process and surface relationships using machine learning, for example. I will also talk about that a little bit. So let's now get into deeper in the in-situ monitoring or process monitoring methods. So what we mean by on-axis monitoring is as follows. We can actually go through the laser beam, through the scanner and f-theta lens to look at the Meltpool and its vicinity through optical techniques. And this is on-axis monitoring. Off-axis monitoring is a lot easier to do it. You just attach a camera that can actually view the base plate and the powder bed and detect various kinds of level of quality predictions. And the vision is that we have an expert system in the machine. And this is also a learning machine because we learn by monitoring layer by layer, part feature and Meltpool, etc. And then it is also a teaching machine because these machine tools are new and there's really little expertise and understanding in the community. And we must produce a lot of data. Data comes from the AM machine, powder bed, embedding, workpiece, and processes. And also we use an approach, this is a holistic view of this machine learning approach. What we have here is the measurement, correct? So that we continuously measure with various kinds of streaming data fusion. And then we have a model with uncertainty because all models have uncertainty in them. And also we have model error as well as measurement error. So this needs to correct itself by using, for example, Kalman filter, Kalman gain type of a control system, and then can be actually attached to an adaptive learning system. So in this respect, we can then talk about process signatures. Process signature, what we call, represents the manufacturing process through which the data are collected from control systems and sensors and can give insights into approaches to control the quality of the final product. In-situ monitoring could identify defects in real time and correct the process accordingly, but this is ideally. And in-situ sensing can improve understanding of the AM process and allow calibration of AM process simulations and increase the part quality. The issue is correlating the process signature with the product quality and the modeling the defects appropriately so that everything is captured. How should the appropriate sensors and their special temporal resolutions be chosen? That's the question. What sensors we must install in order to obtain this data? And then can the in-situ sensing be certified? And what methods and tools should be used for multisensory data fusion? Now here is what we can do. That's the pretty much hierarchical structure for monitoring for quality prediction and process control. At level 0, we are actually using just existing signals at the machine to analyze via statistical machine learning to predict defect of onset from fusing signals. At level 1, we begin to monitor by installing sensors powder bed to evaluate the uniformity of the powder spread geometry to temperature distribution of the melted layer. At level 2, we use monitoring printed layer cross-section and using high-speed videos in the visible and IR ranges. At level 3, we use monitor tracks and evaluate spatter signature and track size and cooling and solidification rate. At the very top, at the very fine layer, that's the level number 4, we monitor the Meltpool size, shape, and temperature. So I think, you know, we should understand those levels, and use appropriate ways of implementing monitoring. So I think monitoring is just not one tool that can be used. There are many, many tools depending on the objective. And quality is all centered around understanding those defects, detecting those defects. Now, can we detect the onset of inaccuracies and defects very quickly during the building process? You know, this is being published in literature by many authors, and we have some geometrical defects. I hope not these days, but definitely still we have internal porosity that we cannot control very well. There are some impurity, contamination, gasification, and then obviously this can lead to crack delaminations, and also understanding of these would be very useful. Now, defect sources and categories are classified by a colleague Grasso and Colosimo in the past, and we can look at the level 1 powder bed monitoring, associated process signatures, powder bed homogeneity, slice geometry, slice surface pattern, and its in-situ sensing methods. For example, we can use primarily off-axis imaging, as well as some fringe projections, etc., to actually do that. What kind of defects can be detected? Porosity, residual stresses, geometrical distortions primarily at that level 1. And level 2, tracks monitoring. We can see hot and cold spots, temperature profile and cooling history, processed by products. Again, by off-axis video imaging, infrared range, we can detect porosity, residual stresses, some level of microstructure and balling and geometrical distortions. At the level 3 Meltpool and spatter monitoring level, we're now looking at the process signature, the size of the Meltpool, shape of the Meltpool, and average intensity profile. And this time, probably on-axis video imaging is more advantageous, on-axis, or accurate, I should say. On-axis pyrometry, and we can actually capture the porosity, residual stresses, microstructure, and inhomogeneity, balling, and surface defect. A lot of things published in level 3 Meltpool and spatter monitoring, but also we need other level of monitoring combined with that. So I'm just going to give you some examples at each level. Signals monitoring, these are existing signals on the machine. This is level 0. We can actually use acoustic emission signal is one of them, looking at if it's meaningful for us to correlate to what's going on that level. And photodetector signal for lack of fusion indicators. You can see this photodetector is actually showing lack of fusion, capturing several times. I think this was a publication where intentionally lack of fusion was created to see the effectiveness of the photodetector signal. Particle count signal is used by counting the particles and correlating at the high and low flow. And essentially, we can say that existing signals, photodetectors and spectrometers measure the light intensity and wavelength from the laser plume, which have been shown to link the volumetric and metallurgical compliances. Powder bed monitoring is also done very much, and here is one study by this author, and then you can see that there is a camera, microphone, and two cameras. You can see those both cameras are off-axis cameras, and microphone is an additional sensor. And powder bed monitoring is done in this case, and then amplitude at the various powder sizes are collected. And then you can see definitely that different powder sizes are correlating to the signal collected, and overall we're able to see the powder bed. Again, on the powder bed monitoring, entire powder bed, we're seeing here is a 3D structured light microscope. In this case, it captures the entire surface of the powder, and then you can see that the powder, in fact, is not flat. It has a distinct topography. So when the laser processes these mountains and deep valleys and trenches, and obviously we cannot expect the same energy density distribution. And eddy current scan is also used, and now you can see here intentionally left a keyhole effect, but eddy current is able to capture globally the keyhole location. And for this, there are this type of arrangements made, off-axis monitoring of using a optical filter as well as light source to visualize the Meltpool area better. And then acoustic emission is also used. This is a study in Switzerland, and in fact it's used to correct the numerical modeling and defect detection by using acoustic sensor as a feedback, and also using artificial intelligence. And at the printed layer monitoring level number 2, we're now looking at tracks layer-wise monitoring, and you can see here a very good picture by this study that using a global sensing technique, we can acquire data on a layer-by-layer basis where the data directly infers a quality condition. A visible spectrum, built area imaging, machine vision captures the top view of the images. And we can see here the tracks forming and different powder layer thickness and layer thicknesses. Here we see a tracks monitoring situation, and here an off-axis again approach is used, and this is two studies, one study from Bitaras, one study from us. Right now it's happening in our lab, looking at the metal surface and looking at the multi-tracks monitoring. And this tells us a lot what's going on track-to-track processing. It doesn't tell us what the Meltpool size is, etc., but we can actually detect by photo signals on the track occurrence. And this is probably the most interesting one because we can see Meltpool monitoring here very closely. This has been studied very extensively in literature. We studied that in 2017 and later, that we used IR videos, infrared thermal videos, to detect the Meltpool and spatter. Here is a very interesting study from Scotland that you can see that they're using particle and cross flow monitoring, and this would allow them what are the particles, number of counts, and how they're related to the quality. The thermal Meltpool imaging captures the infrared byproduct from the Meltpool and the heat transfer heat affected zone to produce a calibrated images of the Meltpool region. And high-speed videos are also used to monitor, again, the Meltpool and the spattered region. obviously there's a lot of image processing needed, and this cannot be done perhaps real time. That's the challenge in this case. So let's begin to get more specific after seeing all those process monitoring techniques and where we are currently and technologically, and look at some studies. Obviously, this requires instrumenting existing AM machines, or if they're instrumented with some on-axis Meltpool monitoring method, that's also fine. Here you can see there is a thermal camera and high-speed frame camera attached to a build chamber to monitor the powder bed as well as the Meltpool region. This is done at an EOS machine at the NIST labs in Maryland in the US, and the powder was in Cornell. And layer-wise laser tracking, as we know, is layer by layer, and typically we have layer rotation. And the part is split into what we call stripes, bands, and each band or each stripe is actually scanned through hatch scanning by a hatch distance, separated by a hatch distance. And that creates some thermal effects as the Meltpool moves, follows the track processing. And to understand this, a design of experiment approach was used by selecting the different power levels, scan speed levels, and hatch distance levels, and looking at building 36 in total coupons, and these are metal cubes, in fact, and understanding the correlation between the process parameters and the build quality. And in this case, we're talking about In-Situ off-axis monitoring and detection method. And camera is in fact detecting the track processing and monitoring the track processing and detecting Meltpool and spatial occurrence. And then we can actually consider three regions of interest: Meltpool area, vicinity of the Meltpool, and the spatter. Then scan pattern is followed, but then we need a high frame rate camera. So this camera has 24,000 frames per second with a reasonable resolution to capture the details. And here is the images of the conditions that where the laser is not in effect, laser is off and laser is on. And then we did some time temporal calculations to analyze it. And later we used a method, Otsu's method of image correlation, to take this raw data, image data offline, and look at the color contour mapping and identify the Meltpool and Meltpool vicinity and spatter by using different gray levels, gray value, pixel intensity value. And here is the simulation model, or actually a processed video. You can see that we're able to monitor by just using a high frame rate camera. This is not infrared, this is not thermal, but by using image correlation and color contour map with a cheap camera, we can in fact monitor the Meltpool and how much heat affected area takes place. What are the, the spatter occurrences? Now, this is not by using machine learning and continuously improving. And we also published this work, and this is a low-cost solution. With this solution, we can actually calculate the Meltpool area, and we can actually calculate the statistical mean, and also look at the data we collect, individual data points, which each data corresponds to the Meltpool area. And then we can actually calculate continuously by statistical quality control techniques, the upper control level and lower control level, and understand the violations, where the violations are taking place. These violations tell us the over-melting and under-melting situation. And this is again obtained with the high frame rate camera. So this can actually be used for process control at a low cost without so much of thermal monitoring. And then you can see that the temporal analysis tells us that overmelting takes place significantly twice during this single track processing, and undermelting follows several times during this track processing. This is a time series analysis, a temporal analysis, and now we're looking at the time signature of the Meltpool and its vicinity. We don't look at the location because the location is going to correlate to where the defects are expected. And we also published that there exists a hot Meltpool type 1 and type 2 cold Meltpool tracks. The hot Meltpool tracks, typically the Meltpool size is larger and begins to get smaller towards the end of the track. At the beginning of the type 2 track, this smaller Meltpool begins to grow, it becomes larger. So in fact, during this enlargement or shrinking of the Meltpool area, we can actually see some violations several times. Then we should expect some defects, at least porosity, to take place in these locations. Now the question is, we understand the time series analysis, temporal analysis, but we don't know where the laser is, where the part location is. To be able to understand the location of the occurrence of these violations, we must actually use a spatial analysis, spatial analysis. In this case, we also use statistics, statistical descriptor based on Hoteling's t-square distance tells us the location on the pixel-wise map where currently the Meltpool is, where the vicinity of the Meltpool area and the spatters. You can see sometimes spatter show 2 peaks, 3 peaks, and 1 peak, or almost no peaks, which means that we can also identify the location during this process. And this is for the type 1 hot Meltpool track monitoring, and this is where type 2 cold Meltpool track monitoring situation. And obviously, when the hot Meltpool, we see more violations. When there's a colder Meltpool in the second type, we see less violations taking place. And now let's talk about thermal measurements, right? The temperature is in fact creating some effects. Like for example, by monitoring the temperature of the Meltpool or its area, we can identify what are the heating and cooling rates are, what the temperature state of the neighboring powder. And again, this is the off-axis sensor camera attached to the door with a installation, and then we're able to monitor the situation with a frame rate about 1,800 frames per second. And this allows us to specifically identify spatter method. Now this is actually a higher resolution than the high frame rate camera data we have. And it's also been used in literature. You can see that we actually take the original image, process it first, remove the lens glare, and then apply the temperature threshold and median filtering, and then begin detecting the particles. Particle detection is very important to identify the severity of the spatter situation. And a lot of people are counting the particles and correlating to the quality or the residual stresses forming. And you can see in the literature similar thing. We can see the Meltpool. This is the scan direction, and this is the tail of the Meltpool. This is the front, and then we have the spatter direction. But spatter could be far away, still taking place. This is a hot Meltpool. This is a cold Meltpool situation because the scan is back and forth. And sometimes we see that the tail begins to produce some spatter, and then sometimes we see very much spatter around the work. I believe for different scanning speeds, low scanning speed 400 millimeter per second, and very high 1600 millimeter per second. And I also believe these authors and this work was published with the work from Finland, in fact. And so probably you're familiar with this work, but it shows us that the situation is different when the laser process parameter changes and the occurrence of step spatter is very different than the previous ones. And what we can actually measure from those thermal imaging is that Meltpool width, Meltpool length, and as well as the spattering particles, right? So the direction of the spattering particles we can measure and quantify. By doing that, we can also measure pixel-wise temperature distribution. This tells us that, for example, we can identify heating and cooling rates extracted from the thermal video. That the heating, this is in fact the cooling situation. The laser is moving away, and then the solidified section is beginning to cool off. This is a heating situation that you can see that the laser is coming to that location, and then it's melting, and then it's leaving that location. So the heating rates are much rapid than the cooling rates, and the cooling rates must be controlled in order for grain refinement and adjusting the microstructure. This is something that we're currently working on in order to actually refine the grains and control the grain solidification and solidification direction by controlling the cooling rates. So monitoring not only actually just tells you the quality defects, can also control the situation. I'm going to start showing some of the offline surface quality predictions, measurements. Here we're looking at a microscope. This is a focus variation microscopy system available from Alicona company. I think now it's Bruker. It's purchased Alicona. And we looked at the cubes produced at different energy densities, different power, scan velocity, and scan strategy rotations, 67 degrees and 90 degrees, orthogonal 90 degrees. And gives us surface texture parameters. Aerial surface texture is measured on the top of the as-built surfaces, and on the side surfaces, these are as-built surfaces facing powder bed in the powder bed. Now, they are different, very distinctly different. Right now, we're looking at this data with a multi-scale analysis with a collaboration with the Worcester Institute of Technology in the US to understand the complexity as well as the relative area effects on the multi-scale analysis. So we obtained the texture parameters. So this is SA, SQ, SSK, and SQ. This is the third and the fourth order, and this is the arithmetic average, and this is the root mean square average. And especially SSK and SQ, skewness and kurtosis, tells us how deep first of all, it tells us if there's a large gap between the valleys and the peaks, and how deep or how high the surface anomalies are. And being able to quantify this to the laser process parameter is important. So we look at the process texture relationships, because these surfaces eventually will define the functional performance of the part, not only microstructure, but also the surfaces that are created by the additive manufacturing process. We can see that energy density reduces the surface texture SA and reduces the surface texture parameter SQ, root mean square. And that's irrelevant of the scan strategy rotation. In both cases, we build and then we see at the higher energy density within the range that we experimented, we get better surface texture. But in terms of the looking at the side surfaces, these are surfaces facing the powder bed in the powder bed. Essentially, it's a little bit of a conflicting situation. We see with the 67 scan strategy rotation, it follows the trend. Energy density has increased, reduces the surface texture parameter, which means that we get better surface quality. But on the other hand, orthogonal actually creates an opposite effect, orthogonal build. So in order to understand that, we use machine learning, two approaches. One is the genetic programming, which is a technique in computer programming. Genetic algorithms are used for modifying and evolving the encoded set of genes, which can also be used for obtaining models for process behavior. For example, you can see here that the surface texture parameter SA, arithmetic average, is actually calculated as function of the process parameters x1, x2, and x3. And neural network, or deep learning, is a multi-layer perceptron feed-forward neural network we use, and then has 3 layers. Input layer, we enter the laser process parameters, power, scan velocity, energy density, scan strategy, rotation. And then we have the measurements, obviously, we train SA, arithmetic average, SQ, SQ, and kurtosis, and then obtain correlations. So you can see that the prediction, offline surface quality prediction, process texture relationship using genetic programming and as well as neural network programming, both actually provide very good predictions. In fact, it's so good, it's very difficult to notice it from these charts. But we can actually go back and look at the comparison. We can see that the genetic programming produces more accurate results in case of binarized categorical value implementation, whereas neural networks outrank genetic programming in case of nominal value implementation. So data analysis and machine learning can actually refine the quality predictions as best as we can. And so I'm going to reach to the conclusion to give a little bit discussion here, and then we can have some question and answer session. So a key component to mainstream adoption of the metal AM processes is developing robust quality control methodologies to take advantage of the layer by layer manufacturing characteristic of AM processes. Many commercial options for sensing exist for both local Meltpool, this is level 4, and global built area, this is level 1, interrogation of the part. So we have really a lot of sensor information. The current challenge is understanding which techniques offer the best performance in terms of quality and seamless integration into the manufacturing operation, because we're confused. There are so many methods and so many other signals available that what to do about it. Now we can identify our research path in three different time horizon. First one is the short-term goals. The second one is the intermediate term goals. Third one is the long-term goals. The short-term goals already happening, improving imaging capabilities. We can see that more and more publications coming out with much refined detection of the Meltpool and the spatter and also cross-flow particle counts. Clarifying what to monitor and when to monitor. And always monitoring doesn't mean, for example, a global built area interrogation would perhaps create a flag, red flag, that local monitoring must actually start to see where the correction must be made. And the second thing is setting expectation for assessing what can and cannot be done and establishing calibration procedures. Intermediate goals, facilitating real-time feedback control. Right now, still not happening. We don't have a feedback control or adaptive control in any one of the AM machines, as far as I know. Improving the use of models and statistical analysis to determine the optimal level of feedback. What feedback should we provide? We can say energy density must be changed. Energy density is a composite of power, laser power, scan velocity, and hatch distance. Which one should be corrected in that location and to what direction? Because any input change will result in output change. Improving modeling capabilities to predict and design the process, and advancing fast computations, because we must do this real-time feedback control, cannot have significant processing time in order to provide a feedback, because it might be too late to act upon. And finally, the long-term goals should be improving the fundamental understanding of the processes, because statistical methods, monitoring, machine learning can help correct the situation, but it cannot drastically change and correct the situation. The drastic change may come from better powder spreading. The drastic change may come from better powder quality control. And the drastic change may come from better setting up the process and the build job and training users, especially for varying shapes and materials. When the new material comes, there is really a large knowledge gap that must be closed very quickly. And also designing the processes to be consistent across machines and sensors. For the large organizations, companies, they have machines in different locations, and you have a research machine. When you actually adjust the process parameters and the certification, but it doesn't work in the other machines. The sensors must be continuously calibrated, machine must be continuously calibrated, so it becomes an issue to scale up this processing method that was successful in the lab and take it into production machines and expect the same performance across the machines, across the sensors. That is a long-term goal, and it's still the problem in other systems like machine tools, CNC milling machines, for example. In organizations, some machines actually don't follow the certification done in the laboratory. Encouraging lifelong learning with respect to new parts, processes, and data management. That goes back to our slide where we talked about machine is the expert system is actually learning continuously, but also it's teaching to the new users, correct? So I think, you know, that part is a artificial intelligence effort to encourage lifelong learning with respect to the new parts, processes, data management. As the machine produces new parts and new materials, it will learn that it will become a stronger expert. Then it will actually teach the user how to deal with these parts and materials in the future. Here are some of our publications listed here if you're interested in. They're all downloadable, and we're also continuously producing new publications. Together with my friend Inigo, we're actually creating a special issue on the In-Situ process monitoring techniques and digital twin in additive manufacturing. Thank you very much, and if you have any questions, you can always email me at ozel@rutgers.edu, and you can also actually find me on internet and LinkedIn, and happy to answer any questions if